In this video, we're going to talk about how to evaluate limits that involve radicals where x is heading towards either negative or positive infinity. And by the end of this video, you are easily going to be able to navigate and evaluate the limits shown here in red. The trickier limits are the ones that go to negative infinity, and that's because you are dealing with negative inputs of x. And I'm going to explain to you how you take that into account as you work through this radical. Folks, the reason why this red limit is tricky as x goes to negative infinity is because radicals are like absolute values. You have to be cognizant of negatives. Recall, if you were to do this limit here in blue, you would have to set this up as a piecewise function. You cannot directly substitute x equals 0 here because this function is not continuous at x equals 0. There is a vertical asymptote here. So to evaluate this blue limit, recall, we would have to examine heading to 0 from both the right and left side. Now, if we were to set this up as a piecewise function, the absolute value of x, we would set x greater than or equal to 0, and in that domain, we would use the function as is. So here, if we are evaluating x approaching 0 from the positive side, we would be able to use numbers such as 0.1 over 0.1, and we would get a positive 1 as our limit, heading towards 0 from the right. However, if we were to set what was inside the absolute value here to less than 0, that's in the domain where x is negative, we would then use the opposite function. So here we would take the limit where negative x is used rather than the original function, which was just x. That negative sign is the opposite. So here, when you're plugging in x values less than 0, you're going to use this limit and you're going to get negative 1. We're going to use this same concept up here with this radical. When you are using x inputs that are going towards negative infinity, that's this part of the piecewise function. So that means we will often, not always, be inserting a negative in front of this limit. Another concept I'd like to review, because I think it will help us understand this whole negative sign situation, is simplifying some complex radicals here. So in these first two radicals, if I were to simplify this, recall that the radical has a square root here. That's an even root. So if we were to simplify this, we would say to ourselves, okay, 2 goes into 2 once without any remainder. So we would be able to pull out an x to the first power, and the 3 would remain. This would be incorrect as written, and here is why. Because pulling out that x squared out of the radical resulted in an even root we started with an even root. When we came out, we ended up with an odd root, which is x to the first. We have to designate this as the absolute value of x, like so. If you pull something out of an even root radical and you end up with an odd exponent, you have to employ the absolute value sign. Let's do this next one. Here, 2 goes into 6 3 times, no remainder. So we're going to pull out an x cubed. Remaining in the radical are going to be 7 and y. Because we ended up with an odd exponent and we started with this variable being inside an even radical, we have to use the absolute value sign. Let's do a couple more. Here, we're going to pull out this x to the fourth. 2 goes into 4 twice, no remainder. We have an x squared on the outside, 5z remaining, no need for an absolute value. You ended up with an even root. Last one, if we pull out the x to the fifth, 2 goes into 5 twice, with one remainder, we end up with 7x to the first and y. Again, no need to worry about absolute value signs when you pull out a variable and you end up with an even root. Okay, with that introduction, let's go ahead and evaluate our first limit. So folks, we have this limit with x going to infinity, and this is basically a rational function, but we have introduced the radical. So first we're going to approach this like we do rational functions. And the way we do that, recall, is to divide both the numerator and denominator by the highest exponent in the denominator. So here I'm going to divide everything in the denominator by x over 3, and in the numerator I'm going to simulate that by multiplying by 1 over x to the 3. Now, I'm also going to anticipate taking this x to the 3, which is currently outside of the radical, and inserting it into the radical. When I do that, I take that x cubed and I square it, and it becomes x to the 6th. Rewriting everything, I now have in the denominator, we have this going to 0 because this denominator is getting very large, and this going to 1. With respect to the numerator, we have x cubed going in as x to the 6th. And the way I think about it is this exponent, as it goes into the radical, always gets bigger. So that's a reminder that you're going to go ahead and square that and get x to the 6th. Because recall, x to the 3rd times x to the 3rd, when you're multiplying and the bases are the same, you add the exponents. Now, very important. When you do this maneuver, when you bring this x to the 3rd into the radical, you have to take a look at your domain. Here, x is going to infinity. These are all positive values. So you do not need to worry about all that absolute value information that we were discussing a few moments ago. When you take the x to the 3rd and place it in, and it becomes x to the 6th, specifically, you do not add a negative sign because all your x value inputs will be positive. Okay, so let's see where that takes us. We now have x to the 6th being used to divide both of these terms inside the radical. So that's going to get us 9x to the 6th over x to the 6th minus x over x to the 6th all over 1. This is going to go to 0. This is going to cancel out. And we're going to end up with the square root of 9 over 1, which equals positive 3. Our next limit involves x going to negative infinity. Again, alarm bells go off. We may have to add a negative depending on what transpires. We're dealing with a rational function essentially, with our denominator involving a radical. We're going to divide both top and bottom by the highest exponent in the denominator. However, when we see x to the 6th, because it's within a square root, we're going to be dealing with x to the 3rd as our highest degree in the denominator. We're going to divide top and bottom by x to the 3rd. So here we're going to have 1 over x to the 3rd out front of this radical. We're going to anticipate moving that radical within the radicand. So I'm going to create a little fraction here. As we move that x to the 3rd in, it's going to become x to the 6th. Remember, as we go in the radical, we get bigger. We do x to the 3rd squared to get x to the 6th. However, because this is an odd exponent outside of a even radical, and because the inputs are negative, we're going to go ahead and add a negative out in front of that function. Okay, let's see where this takes us. Okay, so up top, these are going to cancel out. and we're going to end up with 1. So everything we're dealing with is going to be in the denominator. All right, so we're going to have in the denominator x to the 6 over x to the 6 plus 4 over x to the 6th. This is going to go to 0. This is going to go to 1. So we're going to end up with the square root of 1 over 1, which is just a positive 1. However, because of that negative, because of the negative we inserted, due to the bringing in an odd exponent into the radical, our final answer is going to have a negative out front. So in the end, the answer to this limit is going to be negative 1. Our next limit involves x going to positive infinity. We're not going to have to worry about inserting a negative potential. We're going to divide top and bottom by x raised to the greatest power in the denominator. It is not going to be 2. That 2 is within a radical sign. We're going to use 1 over x to the first to multiply the bottom, and we're going to divide the top by x to the first. As we rewrite our radicand, we're going to anticipate bringing this x to the first into the radical. It's going to get bigger. It's going to be x to the first squared. We're going to use the power rule, so we're going to bring in an x squared into the radicand. If this was going to negative infinity, we would be inserting a negative out front because that's an odd exponent going into an even radical. As it turns out, as I mentioned, we do not have to do that. We end up with this format. Here on top, this is going to go to 1, and that's going to go to 0. So we're going to have 1 in the numerator. In the denominator, this is going to go to 1, and that's going to go to 0. We're going to have 1 in the denominator as well. Our final limit is going to be positive 1. Our next limit involves x going to negative infinity, so we may potentially need to add a negative. We're going to divide both top and bottom by the highest degree in the denominator. That's going to involve multiplying the top by 1 over x to the first power. We're going to build a fraction within the radicand in anticipation of inserting that x to the 1 into the radical. On the bottom, we're going to have these x's cancel out. This is going to go to 0. We're going to have 2 in the denominator. Now, as we insert this x to the first into the radicand, it's going to become x squared, because x to the first raised to the second power is going to give us x squared. Because that's an odd exponent and our inputs are negative, we are going to add a negative in front of this function. Focusing on the numerator, we're going to have x over x squared plus 5x squared over x squared. And we're going to have 2 in the denominator, and we're going to have a negative out in front. Within the radicand, these are going to cancel. This is going to go to 0. We're going to have negative square root of 5 over 2 as the final answer to this limit. In our next limit, we are going towards negative infinity. The highest degree in our denominator is x to the first power. We're going to divide everything by x to the first power in the denominator. In the numerator, we're going to multiply by 1 over x to the first, rewrite our radicand in anticipation of accepting this x to the first into its denominator. In the denominator, we're going to have 0 and a minus 1. This is going to go to minus 1. Now, as we insert that x to the first, because it's an odd exponent and we're coming into an even radical and our domain involves inputs of negative, we are going to add a negative to this whole situation. We bring this in as an x squared. In the numerator, we are going to have these canceling out. We're going to have the square root of 4. This is going to go to 0. And in the denominator, we have negative 1. This is going to equal a negative. I'm going to have 2 in the numerator, because the square root of 4 is 2. Sorry. 2 in the numerator, a negative 1 in the denominator. This is going to become negative 2. However, that negative is going to change our final answer to this limit to positive 2. Okay, in our next limit, we are going to negative infinity. We have a little bit more going on. We are not going to use the conjugate method. We're going to continue with the method that we've been using throughout this video. We're going to divide top and bottom by x to the first. That is the highest degree in the denominator. In the denominator, this is going to go to 0. These are going to cancel out, and we're going to end up with negative 3 in the denominator. Now let's focus on the numerator. We're going to multiply 1 over x to the first times both of these radicals. We're going to build a fraction in anticipation of bringing in that x to the first into the denominator of the radicals. Okay. Now, keep in mind, we are bringing in an odd exponent into a radical that has an even root. This is a square root. Our domain involves inserting negative numbers. That means we need to insert a negative here, and when we deal with this function, we're going to be doing the same thing, so we're going to insert a negative there. This red negative is the original negative that was presented in the problem. These negatives were inserted due to the fact we are dealing with negative inputs in this domain, and we are bringing an odd exponent into an even root. Okay, so this is going to involve having x to the first inside the radical. Out front, we're going to end up with this being 0. I'm sorry, I should have brought it in as x squared. My apologies. That's going to be 0. This is going to be square root of 4. So we're going to have negative square root of 4 out front. And then we're going to have a negative. We're going to have a second negative. And here, this is going to cancel out to 0. This is going to cancel out to 1. So we're going to have negative square root of 1, which is negative 1. These are going to become positive. This is going to stay negative 2 plus 1. Again, this is all within the numerator. This negative 2 plus 1 will give us negative 1. Combined with the original negative 3 in the denominator, our final answer to this limit is going to be positive 1/3.